Eric Rexted, University of St. Andrews, having a look at the solutions to the fourth exercise in the distance sampling in R unit of the online distance sampling workshop. This was an analysis of line transect data using conventional distance sampling in a multi-species survey context. So the purpose of this exercise is to show you some data manipulation necessary to properly account for effort associated with transects on which a filtered data set of a species does not occur. I'm not going to remind you of the data themselves or how to read them in. You've seen these flat file formats before. The interesting thing here is that the study design had 19 transects in that Montrave study area. It's a multi-species survey. You'll see that there were as many as 156 detections of wrens and differing numbers of detections for the other three species. As I said, the focus of our attention in this exercise is to look for situations in which, when we subset our data by species, we find circumstances in which those species are not detected across the entire study area, across all transects. For example, the chapfinch was detected on all but one of the transects. If we filter on chapfinch, we would lose the effort associated with that 12th transect, and our density estimates for chapfinch would be incorrect. So it is these areas, it's these zeros in this two-way table of species by sample label that will cause us difficulty. When we subset our data on robins, for example, we find that robins were detected on only 16 of the 19 transects. And so somehow the missing 3 transects need to be found, and the effort associated with them needs to be placed back into the subsetted data frame before being passed to the function ds. As I mentioned to you in the introduction to this exercise, most of that work is associated with identifying the missing transects. In this case, robins were not seen on transects 11, 16, and 19. Those are the values that miss.lab has taken on. And so we need to find the data associated with those transects and supplement or augment our filtered data set to take those into account. We now have NAs not applicable for the perpendicular distances, the species label, and the visit number. Once those records with the NAs are incorporated into our data set, we can then analyze them. So here's what our histogram for our robin data set looks like. Here are the 3 models that we fitted to the robin data. And the result from this clever little summarized DS model table is this. We see all three of the models fit the data according to the Kramer-von Mises test. We also notice that they produce very similar estimates of P sub A. If they produce very similar estimates of P sub A, they'll also produce very similar estimates of abundance or density. And we see that the delta AIC score is less than 1 for all three of them. So there's very little in it to select between these candidate models for the Robin data set. We needn't necessarily anguish over what's the most appropriate model for these data. In effect, they're all suitable. Just for review, we're going to visit the DHT elements of these model objects. We did this in both exercises 1 and 2, but we'll take another little visit to it. As I just said, given that P sub A is very similar across the three candidate models, I predict that the density estimate will be very similar across the three candidate models. And so what I've done here is I've essentially combined the estimates of density, one per row, for each of the three candidate model sets. And when I take a look at that resulting table, indeed I do find that the density estimates produced by those three different candidate models all produced very similar estimates of density, very similar in the context of the amount of uncertainty associated with each of those point estimates. Goodness of fit, we're going to do a goodness of fit test on the uniform cosine function, detection function. Yes, they are exact distance data, but just as a demonstration, I'm going to specify a set of breakpoints that I'll use for the chi-square goodness of fit. And notice I don't make the widths of all of these bins equal in size. The first one's 12.5 meters wide, then 10 meters wide for a number of intervals, now 15 meters wide, and then the last one something like 12.5 meters wide. So when I invoke GOF-DS, I can specify the breaks I want to pass along to the chi-square test, as well as the QQ plot. QQ plot gives me no cause for concern. And just to demonstrate the consistency between the chi-square goodness of fit results and the Kramer-von Mises goodness of fit results, I see the Kramer-von Mises test also suggests that there's no reason to doubt the adequacy of the uniform cosine model for these data. You'll recall one of the objectives of this exercise was to look at several different ways of plotting the data. Notice this call, without any arguments, allows the plotting function to make its own decision about where the histogram breakpoint should be. Here, I've specified what the breakpoints should be for my purposes. I've also asked that the individual detections not be delineated with show points equals false. And I've introduced a bit of shading here to make the plots a little more handsome. Remember, I showed you how to build functions. There's nothing particularly interesting about, I'm not going to speak to the functions themselves, What I am going to speak to, however, is the result of calling those two functions out here in the right-hand margin. And so by executing these, whatever it is, 6 lines of code, those 6 lines of code produced these 3 plots, one for each species, without my intervention. And you'll notice that without my intervention, I've ended up with what looks like a uniform cosine for the robins, what looks like a half normal for the chaffinches, and a hazard rate model for the wrens. All that was done in an automated fashion without my handiwork, because model selection was being conducted at the same time all of the different models were being fitted. So I hope that shows you something about the utility of doing analyses in R, because it does allow some degree of automation. Note that doesn't replace scrutiny of your models individually, but it can lead to some savings. So I hope that's been useful for you in learning how to do some slightly more elaborate analyses of distance sampling data using R.